because I was just feeling so wiped. And so went over last week and this week. And then, and about the program review, blah, 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 I went, yuck. So that ate up time. All right. I forgot to bring in the announcements. There are several that I saw over the weekend, but I wasn't at a printer to print them out, so I don't have, but I do know they are, the math team is meeting Fridays at noon and Mondays at 3, okay, on the Birmingham campus. If you want to meet any out here, I'll be glad to meet with you during my office hours, at least as much as I can. I'll put it that way, because I'll go over this other stuff. We are recording now, so let's get set up for the slideshow, and I'll sort of explain a little bit of what's going on. If you were here last week, you might have remembered I wasn't in the best of shape. I had a treatment, new drug they were trying on Thursday 10% dosage, and then Friday 90% dose. And then last week, I was just white slick. I was just exhausted. The best word for it was fatigued, I found out, because my wife's an epidemiologist. She looked up some of the side effects of the drugs and stuff, and that was number one, fatigue. Okay. And then when I had my second round last Friday, a full 100%, Terrell is here, I was supposed to have labs first, and I did, but they said it's not going to bother the treatment. You're going to have treatment anyway. It's not going to count on that, but they just want to see how the first round went. Well, normal range for white blood cells, it's a B-cell malignancy, are 7 to 11,000, okay? My white blood cells before Thursday's treatment, a week ago, were 128,000. Okay, so considerably higher than, more than 10 times what the max should have been. When I went in, when they did the treatment last time, they had already started the treatment. When I got the blood work back, 1.1 thousand. They were below where they should have been. I mean, that drug was fantastically effective. But on the other hand, it also dropped down my red blood cells, my hemoglobin, my hematocrits. That's why I was exhausted, plus all the other stuff going on inside too. But they went on and continued the treatment last time, so I'm probably going to be a bit fatigued this week too, but so far, knock on wood, not as bad as last week. So I may get the dragging some, but if so, just bear with me. Okay. Now, let's talk about, I have my arrow at a weird place here. Example 2 was not on the slide set, and I think we did it here, but I think I ran out of time before I ran out of problems. So let's go back and just quickly do example 2. We had started on that, right? It's not on the slide set. I was just doing it here. If this is too redundant, let me know. Like I said, last week I was so wiped out, I can't remember what we said and what we didn't, but I put my mark here. It says, find the slopes of the tangent lines to the graphs of f of x equal, sorry. Any questions on anything we've done so far? And by the way, I can't remember, again, everything last week was sort of a fog. I know I had the test made out, and I had it copied, but was it in time for class last time? Did I pass out to you? I did pass out the test. Okay. Okay, good. Okay. I couldn't remember for sure if I knew the copy room was backed up, and I couldn't remember if I got it in time for you or not. So anyway, anytime you have questions, I won't work a test question in class, but I'll work anything similar to it from the book. So go to the book, find those. That was covering most of chapter 1. Now, I don't think I gave you the breakdown of those. Would you find that helpful or not? which questions came from? Yay or nay? Okay. 1.1 would be questions 1 and 2. Wait, I'm sorry. No, 2. Yeah. Let me get back in. Yeah, 1.1 is questions 1 and 2. I think 3 and 4 are 1.2. 5 and 6 are 1.3. 7 and 8 are 1.4. And 9 and 10 are 1.5. So it's from each section 2 questions in order. Now, does that mean you have to do them that way? No, if you can do it analytically, even though it's from the section we did it graphically, fine. I mean, go for it, you know. But if it is from that section, this is my first time teaching from this new text, okay? And the test bank has lots of tables and graphs and it's multiple choice, and I just don't find that particularly, well, number one, since there's something else. The test bank did not translate very well, even though it was supposed to be in Word. It was a miserable. Word does not interact well with things, I found. And I could not do any modification to the questions, and they were taking pages and pages. So I had to retype it all. And since I had to retype it all, I didn't want to do graphs and tables and everything else. But I thought those are simple enough questions. And if you need to do a table, do a table. You know, that's how we did it in class and in the text. If you if it's helpful to do a graph, do a graph. You know, do whatever it takes so you can see what's going on. But basically, most of them can be done, not all, but most of them can be done analytically. Those first 2, you almost have to set up a table and see what the slope is becoming. But if you have questions, bring those to class next time, or if you have them now, I'll field them now. But again, I'll do anything. I'll clarify any question on the test, but I'll work anything from the book. I won't work a test question in class, because that's obviously a test question. All right, enough of that. Any other questions? All right. So find the slopes of the tangent lines to the graph. F of x is equal to x squared plus 1. So here is, let me get my pen set up. And again, I probably already said this, but part of the thing this week is I have an almost constant headache and my throat's sore too. I think I talked too much yesterday or something, because so if I start having difficulty speaking or something, that's what's going on. I hope it won't be. I hope my head doesn't get out of control either. All right, here's the function. F of x is equal to x squared plus 1. Okay? It says find the slopes of the tangent lines at 2 points. The first of these points are at 0, 1, and the second one is at -1, 2. And I'm pretty sure I went over this last time. Whenever I'm given a problem like this, first thing I do, because I'm such a cynic, I want to make sure those points are on that graph. Okay? Are they? Is 0, 1 on that graph? Sure. You plug in a 0 for x, and you get f of 0 equal 1. How about -1? Yes. F of -1 squared is 1 plus 1 is 2. High-level math. Okay? So both of those points are on the graph. Okay? And it says find the slopes of the tangent lines. Now, what gives you the slope of the tangent line? The limit of what?
Limit of x squared plus 1.
Say again?
Limit of x squared plus 1.
Okay. Pretty close, not quite right. It's the difference quotient of that function. Okay. Remember, the difference quotient is rise over run, slope. Okay. So the slope of the tangent line is going to be that, and it will be a limit because your run, the delta x, is going to 0. Now, of course, for it to have a slope, delta y's got to go to 0 too, so you have the indeterminate form. If the delta y stayed at 7 and this went to 0, not going to have a slope. So, so we're going to do the difference quotient. Can anyone remind me what that difference quotient limit is? I'll start at LIM.
Limit x approaches c.
Of what?
X approaches c.
Oh, okay. F of
C plus delta x.
yeah. They're using C, okay, plus delta x minus f of C divided by delta x, okay? What's the limit doing? Delta x is going to 0, okay? Now, what is the C here? Most of the time, yeah, that's not a the way I would be describing it, but so what is your C here? That's a little bit different, but it's correct. What is your C? Yeah, those would be your x variables. At first would be the 0, then later it would be a -1. Those are the 2 points. So the C is the x value. That's why I would have said f of x plus delta x minus f of x divided by delta x, and then done this, plugged in x equals c. So they're doing it a little backwards. So first thing we've got to do to calculate that limit is what? F of c plus delta x. That's what we need to evaluate first. And what would that be? A little louder? Okay, not just delta x. You plug in, instead of the x, c plus delta x. Plug it in here. So that would be c plus delta x squared plus 1, right? And what is c plus delta x squared? Anyone remember the c squared? Say again?
Plus 2 delta x.
Excellent. Plus 2c delta x, right? More? Plus delta x squared. Okay? And then you got plus 1. Okay? Pretty mean, ugly looking, but it's there. All right? Next thing we need is to know what f of c is. Well, what is f of c? Say again? Let's hope not. Oh, you're already plugging into 0. Don't do that yet. Plug it in here. What is, instead of x, put a c. What does that give you? Everywhere you see an x, put a c. C squared plus 1. Very good. Now we got to do the difference of those two things. Okay? So this will be the limit as delta x approaches 0 of your f of c plus delta x was this c squared plus 2c delta x plus delta x squared plus 1. That's the f of c plus delta x. And now we've got to do minus f of c, which is c squared plus 1. Now, I wrote it that way so you can tell this entity is what follows the minus sign, the entire entity. Okay? Hate to take up an extra line to do it, but I think to begin with we can. All over delta x. So that will now be the limit as delta x approaches 0 of c squared plus 2c delta x plus delta x squared plus 1, and now subtract. Distribute that minus sign across the parentheses. Minus c squared. What's next? You may have said it. I don't hear well. Minus c squared. Say again? Minus 1. Perfect. All over delta x. Yeah. What do we notice we can do here? All right, there's some like terms that we can combine. Here's a c squared. Minus c squared adds a 0. I like that. Next. Plus 1 minus 1. That adds a 0. So that gives us the limit. I'm doing extra steps here just to make it obvious, I think, of 2c delta x plus delta x squared divided by delta x. Okay? And here's Jeremy. I can find you. There you go. Okay. Yeah, got it. Okay? Now, what do you notice you can do now? Yes, factor out a delta x. Okay? Okay? From numerator and denominator, and that would give you, I'm running out of room rapidly. Let's see if I can get it in here. The limit as delta x, if I could write, goes to 0. We're doing example 2 near the bottom half of page 102 in section 2.1. And by the way, since some of you have come in since we got started, if any of you did not get a copy of the first test last week, pick it up today. Okay? All right. That's pretty ugly under that limit here. But we're going to factor out a delta x. And what does that leave you with in the numerator? Say again? Two. No, you already factored out a delta x. 2c. Huh? Plus delta x. Okay, very good. All right, over delta x. Now, what good news comes out of that? Yes, delta x over delta x is 1. And why is that good news? Because what you had was a delta x going to 0, which was a pain in the neck here, and here, and here, and here, because you can't divide by 0. But these were indeterminate forms, not undefined forms. Once you get rid of the delta x, now you have a limit you can evaluate and break your knee. Okay. That would be limit as delta x approaches 0 of 2c plus delta x. Now what's the limit of that as delta x goes to 0? The delta x is 0, but what do you have left? 2c, exactly. That limit is 2c. Now you can plug in any value you want to. And remember, the domain of this function is all real numbers. We were interested in 2 places, so when you plug c equals 0 in, what's your limit? 0. The slope of the tangent line is 0, and when you plug in a minus 1, negative 2. There's your slope there. Now, you'll see in the text the tangent line at, I guess I'll autograph this. It's going to be ugly. Y'all are used to that now, aren't you? But don't answer that question. Okay, here is 1. We'll do 2, 3, 4, 5. Okay, we won't need all those. At 0, we're at 1. At 2, we're at 1, we're at 2. At negative 1, we're at 2. At, oh, I guess I should tick in a few down here. At 2, you're at 5. 2, 3, 4, 5. That's about as far as we need to go. And over here, there too. There's what your graph of your function looks like, right? And at 0, 1, sure enough, the tangent line is a horizontal line, slope of 0. Okay? So at this point, your slope is 0, And at this point, negative 1, 2, your slope is minus 2, going downhill fast. Okay, and in fact, I even drew it close to the right place. So there's your slope at negative 1, 2. Any point on that graph, at 1, 2, that would have been a plus 2. Up here, that would have been a plus 6. Over here, that would have been a minus 6. Plug in any value for C. That's why I like to call it X, not C. And you get your slope of the tangent line at that 0.5, 0.73. You know, whatever you want to put in there, you know, you'll get the slope of that line. Does that make sense? All the slopes on the negative side are going to be negative slope, 0 at the bottom, and positive slopes getting larger and larger as you go up. Does that make sense? Pretty nifty, huh? All from your limit of your difference quotient. Okay. Diamond, right? Find you in here. All right, good deal. We just finished example 2 on page 102, bottom half of the page. So the slope at any point, C, f of C, for this graph, f of x equal x squared plus 1, the slope, the m, is 2c, just like we found right there. And whatever c you put in there, you'll have it. All right, now, the next thing they're going to show here, do I need to leave that up a little bit longer, or everybody got it? Okay, I was trying to see where this, I'm going to erase this so I can read it better. Okay. Ah, there it is. I see that. That paragraph right here, or portion of a paragraph, sentence or two, I guess it is, one sentence, pretty long sentence. Okay, hold on that for a second. Nope. All right. I wish they showed this. Oh, here it is. I guess we already did this one. The definition of a tangent line to a curve does not cover the possibility of a vertical tangent line. Why would that be the case? Remember what your limit is, change of y over change of x. You're letting the change of x go to 0. And as long as that becomes an indeterminate form, you can calculate the derivative. But notice here, when your delta y here is getting smaller as your delta x is, look at what's happening here. That delta y is going to be a large number, well, relatively large number, whereas the c is going to 0. The delta c, x is going to 0. So yeah, this would give you a vertical tangent line which has a delta z of 0, but your delta y, or your delta x of 0, your delta y is going to be infinite. No, not defined. That's a good old not defined case. Okay? So that's why that one doesn't work. Okay? We probably hit that last time. I don't remember. Again, everything was really fuzzy last week. Not too great this week, but it's a lot better than last week. So here we hear the, this is part of that last paragraph at the bottom of the page, right after that vertical tangent line. This says, when the domain of f is the closed interval a to b, not the open interval, some closed interval a to b, you can extend the definition of a vertical tangent line to include the endpoints. Why would they say a vertical tangent line? By considering continuity and limits from the left and from the right, x equal a and x equal b. I'm not sure why they even have that in there, okay? it just looks out of context here. When the domain of f is a closed interval, you can extend the definition of a vertical tangent line to include the endpoints by considering continuity and limits from the right, x equal a, or from the left, x equal b. I think I know what they're getting at. They're just not very clear. Okay? The square root function. Square root function, remember, looks like a sleeping half a parabola, right? It's not defined for any x negative, right? But it is defined at x equals 0. Okay? Anywhere other than x equals 0, there is a slope of the tangent line. But when you get to x equals 0, you get a vertical slope. And I think that's what they are meaning there, but boy, it just seems to be from nowhere. Okay, I think that's what they're talking about. Okay, so let's move on to the derivative of a function. Okay? You have now arrived at a crucial point in the study of calculus. Okay? The limit used to define the slope of a tangent line is also used to define one of the two fundamental operations of calculus, differentiation. This is what we're talking about. Think of it. Difference quotient, differentiation. They sound pretty similar, don't they? You're talking about differences here. Okay? So differentiation. The definition of the derivative of a function, this is on your top of page 103, the derivative of f at x is precisely this f prime. Now this is a new notation, I guess. I don't know if y'all are familiar with it. That means the derivative, the first derivative of the function at the point x is the limit as delta x approaches 0. This is going back to the form I like. F of x plus delta x minus f of x over delta x. Remember the last one had c's in there, but then they plugged those in for x's. I thought, why don't you put it x's? Okay. Provided the limit exists. In other words, those vertical tangent lines are not going to exist. Okay? And for all x's for which this limit exists, then f prime is a function of x. It's a defined function. If the limit doesn't exist, it's not a defined function at that value x. Okay? So that's just your difference quotient all over again. Now we've given a name to it. Now, there are other names for it. And we're going to spend a lot of time dealing with these names. And don't let them confuse you. It's just that mathematics is pretty precise, but lots of people use mathematics, like physicists and engineers and stuff. And the further you get from mathematics, the sloppier the notation gets. So just get used to it. That's where the real life is. Okay? Now, be sure you see that the derivative of a function of x is also a function of x. In other words, you have some function here. Okay? And then if you take the derivative of that function, you get another function of x. It's not going to look like the same function you had to begin with, but it's going to be related to it. Okay? It's also a function of x. This new function gives the slope of the tangent line to the graph of f at every point x, f of x, just like we saw in that last example, provided that the graph has a tangent line at that point. If it's a vertical line, it's not going to have a thing. The definition can also be used to determine the instantaneous rate of change, or simply the rate of change of one variable with respect to the other. That's why Newton came up with it. I can't say why Leibniz came up with it, but that's what Newton was trying to do. Finding not an average change, instantaneous rate of change of planets moving around the sun, of the moon moving around the earth. He wanted to know exactly what the instantaneous rate of change was in the velocity and the acceleration in the displacement. Okay? That is what your slopes of your tangent lines have. The process of finding the derivative of a function is called differentiation. Okay? And the function is differentiable at x when its derivative exists at x and is also differentiable on the open interval AB when it's differentiable at every point on that interval AB. Okay, that's just, you can talk about it being differentiable at a single point, or you can talk about it being differentiable on an open interval. Okay, both of those are legitimate processes. Okay, now we get to our nomenclature. Don't let it confuse you, but just get used to it. In addition to f prime, which is first derivative of f at x, f prime of x, other notations are used to denote the derivative of f of y is equal to f of x. Well, we said f prime, that's the derivative. This is called Leibniz notation, dy dx. Okay? And if you think about that, think of d as your delta, right? Change of y over change of x. That's the slope. So yeah, dy dx, that says you let the delta go to 0, the delta goes to a little d. So that's where that comes from, dy dx. Now, because f of x is always y, we call this f prime of x, you can also call it y prime of x, okay? Or y prime, okay? Or, since y is f of x, you can put d by dx of f of x. And you don't have to put the brackets down here, you can just do df dx, okay? They left that one out. I found that actually a handier or more usable formula. Let's rewrite that, df dx, okay? And you can put the f of x there if you want to. You don't have to, but you could. Now, the next one we usually don't use until you're further along in calculus, and that's it's introducing, and all these other things are too, an operator. And this is the differential operator. And it basically is taking the derivative of y with respect to x. So that's what this is. We're not going to use that a lot, or I don't know. First time I taught from this book, they may throw it in there way early. But usually we don't use that until higher level courses. Okay? All right. The notation dy dx is the derivative of y with respect to x. Okay, that's how we usually read this. Or simply dy dx. Now, I'm not saying this in any derogatory manner, but it's just something I've noticed. We have several friends who are Indians, sub-Asian continent India, and they typically, to me, talk way too fast. Okay, I have southern ears. I don't understand, and I've tutored a few of the friends of our family, the kids when they were in college and even in grad school, and how they say this is dx. They use that notation, dx. Okay, and I was probably in my second or third tutoring session before I finally figured out what they were saying. But every now and then I'll just throw that in there because I find it funny. It sounds strange, dx. Okay, and that's all right. That's the operator, dx. Okay. I'll try not to do that too much. I won't. Okay. So what is your dy dx? It's the limit as your delta x goes to 0 of delta y over delta x, where delta is difference in y, difference in y over difference in x. As you let that delta x go to 0, it becomes a dx, and the y becomes a dy. Okay? So that is your good old difference quotient. F of x plus delta x minus f of x over delta x. And that's also f prime of x. I mean, all these things mean the same thing. It also is y prime, okay? It's also capital D sub x of y, okay? It's all those things. That's the nomenclature they use for it. Or it's d by dx, okay? Never mind, okay. So let's do example 3. To find the derivative of f of x equal x cubed plus 2x, use the definition of the derivative as shown. Okay? So here we're back doing this. We just got a different function this time. What's one of the first things we're going to have to do then? Using this limit to do your derivative, what will you do? Definitely, okay. F of x plus delta x is going to be, a little louder, x plus delta x cubed plus 2 times x plus delta x. All right, now, I asked before, and y'all were real quick about it, what is x plus delta x squared? You knew that one right off the top. How do you do x plus delta x cubed? Do any of you know? Okay. What you can do is x plus delta x times x plus delta x squared. You already know what x plus delta x, and then you're multiplying and doing out. That's the straightforward way to do it. It just takes several steps. Have any of you ever heard of Pascal's triangle? Okay? I'm going to tell you what Pascal's triangle is. It just makes this kind of thing go a lot faster. Of course, to show you now, I could have done the whole thing in that, but let's just start. Pascal triangle starts with a 1 at the top, and it has a 1 at the edges, and it has a 1 at these edges, but then when you get in here, you add these two 1s together, and you get a 2, right? Okay, then you put a 1 at the edges, add these two together, and you get a 3, and you add those two together, you get a 3. Okay, you put a 1 at the edges, and what would be your interior numbers? 4, 6, 4. Put a 1 on the edges, and what do you get? 5, 10, 10, 5. And you can keep on going as many times as you want to. Okay. Why? What's the big deal here? I'm going to show you something. This is, I'm going to call it a plus b. A plus b to the 0th power. Is that correct or not? What is anything to the 0th power? 1. Okay, yeah, we'll buy that. That's 1, right? This is a plus b to the 1st power, right? These are the coefficients. What is a plus b to the 1st power? A plus b, which would be 1a plus 1b, right? Now, y'all told me this one before. You remember what it is now? A plus b squared. I think Harrison said it right off the top. What was that? A squared. 2ab. Okay, you better get it right. Plus b squared. All right. What are its coefficients? 1, 2, 1. There they are. Can you guess what this one is? A plus b cubed. There are the coefficients. There we have our a plus b cubed, which in this case would be, where is a good place to write it? Here, I guess. That would be x cubed plus coefficient of 3 x squared delta x plus another 3 x delta x squared. If you want to put those in parentheses, you can, plus delta x cubed. Okay? That's the easy way to do what this is called is the binomial expansion. And guess who came up with this? Isaac Newton. Goodness gracious, he did so much. He did calculus, he did physics, he did optics, he did gravity, he did binomial expansion. There's hardly anything he didn't do. I mean, that one mind advanced math and science forever. I mean, a plus b cubed, which would be a cubed plus a squared b, 3a squared b plus 3ab squared plus b cubed. B cubed, yeah. Okay. Those are your coefficients that you have there. Notice what's happening here. The first thing is decreasing in power by 1, 3, 2, 1, 0, blast off. The second one is increasing, 0, 1, 2, 3. The powers on. Okay. And then the coefficients, those are your coefficients. Okay. That part's done, sorry. Or you can multiply them out. You can do it that way too. Okay. We've only got the first part done. What's the next part? Plus 2x plus 2 delta x. Okay. There's our alpha of x plus delta x. Okay. Now, the good news is alpha of x is exactly what alpha of x is. That's why you don't have to rewrite it again. So let's do what alpha prime of x is. That's the limit as delta x is approaching 0 of, let's write out what your f of x plus delta x is. X cubed plus 3x squared delta x plus 3x delta x squared, and if you want to put that in parentheses, you can, plus delta x cubed, and you might want to put that in parentheses too, reminding yourself it's not delta x cubed, it's delta x cubed, okay? Okay, plus 2x, I'm going to erase Pascal's triangle, is that okay? Well, I don't care if it is or not. No, I'm just kidding. It's, otherwise I don't have enough room to write. And it's already so messy, right? Don't answer that question, okay? All right. All right. Where was I? Plus 2x plus 2 delta x. Okay? That was our alpha of x plus delta x. Now we got to subtract our alpha of x, which is x cubed plus 2x. Okay? And all that's over delta x. Okay? And the limit here as delta x is approaching 0 of, now, I hate to write that whole thing again, but I think I will till you sort of get used to it. That'll be x cubed plus 3x squared delta x plus 3x, that's a 3, delta x squared plus delta x cubed plus 2x plus 2 delta x, and then what does that following parentheses become? Minus x cubed minus 2x, right? All over delta x. Aren't these fun? Okay. Now, what do you do next? Combine like terms. Excellent. What like terms do you see? Okay, here you have an x cubed minus x cubed. You have to stretch your eyes all the way across there. Those add to 0. What else? Two x and minus 2x. Those add to 0. So what we have left here is 3x squared delta x plus 3x delta x squared plus delta x cubed plus 2 delta x, right? All over delta x. And what do we notice here? What can you do next? Yes, let's factor out a delta x. Limit as delta x approaches 0 of, let's factor out a delta x, and what are you left with? 3x squared plus 3x delta x, you got rid of one but not the other, plus delta x squared plus 2. Okay? All divided by delta x. And now what can you do? Divide out the delta x's. You're absolutely right. And now you can take that limit because you no longer have delta x in the denominator. Good news, folks. And what does that give you? As delta x is approaching 0, that stays 3x squared, right? There's no delta x in that, but that now goes to 0. That goes to 0 really fast because you're squaring it, and you're left with a plus 2. Ta-da! There is your derivative. To find the derivative of f of x, use that definition, and this is your f prime of x. Right there. 3x squared plus 2.
When you're doing these kind of derivatives, it's gonna always go to like exponent going down. I got like 3x squared.
Very good observation. Yeah.
It's gonna always go like that. And then the x, like it was 2x
Okay.
squared, it'd be 4x.
Let me answer that question. With polynomial functions, yes. Okay, we've got lots of other functions we'll be messing with. For polynomials, you're absolutely right. And actually, for a lot that are not polynomial functions, you have to be pretty careful with, like 1 over x. That's going to be x to the minus 1. It's going to go down 2, but that goes down to x to the minus 2 because it's decreasing. So, yeah, it's still going to be doing that. So, yeah, you're hitting right on the money. Good insight. Excellent insight. Way to go. And since you're thinking that way so cleverly, I hate to do this now because you'll never want to do another limit. Not that you want to, but yeah, let me show you something. Where was it? Oh, I erased it all, didn't I? Okay. Now this is one we did last time. Okay. What did we wind up being our derivative here? F of x equal 2x plus 2x minus 3. It was going to be 2. Okay. The x went down 1. Yeah, and the constant, there's nothing following that, so it has nothing. So that derivative is 2. Okay, now, I thought I left it on, and there, sure enough, the limit is 2. 2, okay. Slope is everywhere, 2. Okay. I erased it, but remember when we did example 2 before, and we did f of x equal x squared plus 1? You remember what that derivative was? You're absolutely right, 2x. Okay? Your power went down by 1, but your coefficient became a 2. Okay? Yeah, okay. And then the one we just did, okay, really hate to do this because you're going to ruin doing limits from now on. What would that be? 3x squared plus 2. There it is. Okay, you just found the shortcut. Okay, for polynomial functions. And we'll find out other functions will work too, but we got it in. As functions get more and more complicated, we get more and more rules. But for polynomials, they're beautiful. The power goes down by 1, and your coefficient times your exponent times your coefficient. Ah, boy, it's nice. Really nice. You'll never want to do another limit in your life, will you? Yeah, of course you will. You love doing limits. Okay. Especially on tests. Okay. What's that? All right. Sorry, I shouldn't have shown you that, should I? Okay, so that's example 3. And by the way, example 3 is also at larsonprecalculus.com for an interactive version of that kind of example. So you've got some more things to look at if you want to. But we wound up with 3x squared plus 2. Good insight there. Let me go on and erase all this, and let's see how they did it. Well, they did the limit as, and then what they had to do was alpha of x plus delta x, which would be x plus delta x cubed plus 2 times x plus delta x, minus alpha of x, which would be minus x cubed plus 2x, all over delta x. And that first one, now they didn't show you how they got it, they just threw it up there, okay? Now if you don't remember the Pascal's triangle, by the way, Pascal could be a good paper topic, or how did he develop his triangle? That could be a good paper topic, or Newton or Leibniz or any of these things could be. You've got lots of things to choose from. Just don't forget about your papers, okay? All right, so when we did this, all right, x cubed plus 3x squared delta x plus 3x delta x squared plus x cubed delta x cubed plus 2 times x plus 2 times delta x minus x cubed minus 2x all over delta x. And then, as Diamond pointed out, we have some things we can combine like terms. The x cubes go out and the 2x's go out. Okay, they've been dating. Okay, so what you're left with is 3x, the limit is delta x approaches 0, 3x squared delta x plus 3x delta x squared plus delta x cubed plus 2 delta x all over delta x. Then notice you got common factors of delta x in every term in the numerator. And what happens then, factor it out, and you have 3x squared plus 3x delta x plus delta x squared plus 2. And when the delta x's divide away, then you're left with something you can take a limit of. The limit as delta x approaches 0 of 3x squared plus 3 delta x plus delta x squared plus 2. And when delta x goes to 0, that goes to 0. And that goes to 0, you're left with 3x squared. Right? That's what a derivative is. That's why we did all of chapter 1 on limits, so we could do a derivative. Wasn't that fun? Okay. Do it. Okay. Get that test knocked out. 3x squared plus 2. All right. That was example 3. And again, they have the LarsonCalculus.com has an interactive version of that type of example. Now, they skipping examples 4 and 5, so let's do these. Okay? Okay. Okay. Find f prime of x when f of x is equal to the square root of x. Okay. I told you, you got some that are not polynomial functions. They're going to be a little bit bigger pain in the neck or other body parts. Okay. So what will this be? What we're looking for is f prime. And what is our definition for f prime? Say again? The limit? Is that what you're saying? I couldn't hear. Oh, derivative of a function. Yeah, that's exactly what it is. What is its definition? As delta x is approaching 0 of f of x plus delta x minus f of x over delta x. Difference quotient. Okay? So obviously what must we do here? We must first do f of x plus delta x. And what would that be? That's the square root of x plus delta x. Okay? All right, that one wasn't too bad. And we already know what that is, so let's plug and chug. That's the limit as delta x approaches 0 of help me. What is f of x plus delta x? The square root of x plus delta x minus radical x. Very good. All over delta x. A big boo hiss here, isn't it? That's not nearly as nice as a polynomial function, is it? Okay? You can't use Pascal's triangle here. Yeah. So what are we going to do? I want you to notice something first. This is a radical minus a radical. Have we ever seen anything like that before? Well, when we had something like this, especially if that was in the denominator, what would we do to it? Ah, very good. Rationalize it. And how do you rationalize the denominator? Multiply by its second. It's conjugate. Conjugate. Well, this one's in the numerator, but guess what? We're going to do that anyway. Multiply by its conjugate. Okay? And what is the conjugate of that numerator? No, the square root of x plus delta x. That stays the same. Plus the square root of x. Yeah. But if you multiply the numerator by that, guess what you got to do? Multiply the denominator by that as well. X plus delta x plus the square root of x. Okay? Now, it wasn't just for radicals we did this. Remember one of the special products we had back when we were doing polynomials, way back in Math 100 or something like that? If you had a plus b, you wanted a fairly simple expression, multiply it by a minus b. The product of the sum and the difference of the same two numbers, an expression and its conjugate, is the difference of their squares, right? That's what we get here, difference of their squares. So, let's do that. I'm going to start over here. The limit at, not good, okay? The limit as delta x is approaching 0 of, now, multiply the product of those two conjugates together. What do you have? X plus delta x, because when you multiply two radicals, you get what's inside the radical. Minus x. Ah, man, that's nice, isn't it? Ooh, but what you got in the denominator, delta x times the square root of x plus delta x plus delta x. Okay. Whoa. I didn't do my radicals right. I had it right and I messed it up. Okay, this one ends there and that one ends there. Yeah, got it. Okay, now I didn't multiply those out, and I think you'll see why in a minute. So let's go with it. So you tell me what that numerator has become. The limit as delta x is approaching 0 of, that's all you're left with, delta x, because x minus x is 0, over delta x times the square root of x plus delta x plus the square root of x. Right? Okay. Now what do you see has happened? The delta x go away again, don't they? Oh, I like for them to lose those because I don't like dividing by 0. It's really messy. So let's see what we got. This is the limit as delta x is approaching 0 of 1 over the square root of x plus delta x. I guess I don't need that parentheses anymore, do I? Let me just get rid of that because it's just messing things up. Okay, plus delta x. No, the square root of x. I can't read my own writing. Okay, you can't either, can you? Guess what we can do now? You don't need to. You don't have a delta x in the denominator by itself anymore, so just like Glade. Plug it in, plug it in. What do you get? As you let delta x go to 0, this gives you 1 over the square root of x plus the square root of x, which is 1/2 1 over 2 square root of x. Okay? That's it. That is your derivative there. Let's see. And that's exactly what they got. Good for them. Okay? Let's plug in some values there. Give me an x. 1. Okay? Now what would that derivative be at x equal 1? That's, by the way, the square root of 1. There's your function. That would be 1/2. Right? So plug in at x equal 1. You got that. What do you notice you can't plug in? A 0, because you can't have a 0 in the denominator. Of course, you can't plug in any negative number because those are not defined. Square root of x is 0 at 0, but it doesn't have a derivative at 0. That's one of those vertical tangent lines. Everywhere else, though, remember that's the graph of the half of the sleeping parabola. Every place else it has a defined thing. Here at 0, vertical tangent line, not defined. Everywhere else it is. All right. Now, Jeremy's the problem child, right? I know Jeremy is thinking, what if we had written this f of x? What's another way to write square root of x? X to the second? That would be 1 over x. X to the 1/2. Now, what if Jeremy would have used his little rule for this? What would that have given us? (1/2) times negative 1/2, and that would be 1/2 times 1 over x to the 1/2, right? Which would be 1 over 2 times the square root of x. Oh, it works there too, didn't it? It did. So not just polynomial functions, but others will do it as well, right? Not the same thing. Oh, I'm taking all the fun out of doing the limits, am I not? Yeah. Sorry about that. I don't mean to do that. I know y'all like doing the limits. Okay? Okay. Make sense? All right. Let's now do example 5. Okay? Do I need to leave that up there a little longer? Or are you okay with it? All right to erase? Okay. Let's do example 5. Now this one also has at larsoncalculus.com, you can get an interactive version of this type of example as well. Find the derivative with respect to t of the function y is equal to 2 over t. Okay? How do you reckon we're going to do that? We're looking for the derivative, which we could call as y prime. That's one name for it. What would that be its definition? Help me, help me. I'll start it. The limit. Yeah, let's call it delta t this time. is approaching 0 of I'm flopping around notations on you just to get them used to it. You can call this y of t. So this will be y of t plus delta t. That makes sense? I know I'm getting real sloppy with the notation, but get used to it because lots of people use different notations. Minus, no, just y of t, right. Okay, all over delta t, you got it. Okay, now what is your y of t plus delta t? A little louder. 2 over t plus delta t. That's it. Okay. All right. So there is your y of t plus delta t. And then you know what y of t is. So let's do our limit. This is the limit as delta t is approaching 0 of, okay, 2 over t plus delta t minus two over t over delta t. All right. We love our fractions, don't we? Of course we do. Always have. Okay? How are we going to subtract those two fractional forms? Yeah, got to get a good old common denominator. What's common denominator going to be? T times t plus delta t. Now, all right. Okay. Now, all I'm doing is a fractional form here. The product is going, the least common denominator is the product of the two, so our new least common denominator is going to be t times t plus delta t minus, and this will be t times t plus delta t. I know this looks weird. And the first thing had a 2 here, and to get that common denominator, which is the product of the two, what did I have to multiply this by to get this? T, okay? So that is going to be 2t minus, and what did I have to multiply this denominator by to get this? T plus delta t. And I already had a 2 up there from here, 2 over t, so I had to multiply that by t plus delta t. My writing stinks. Sorry about that. Get over it. Okay. All that's divided by delta t, right? So that limit as delta t is approaching 0. All right. We've got our common denominator, right? So what we do is keep that common denominator, and subtract our numerators, right? Okay. So in the numerator part of that, least common denominator is our t times t plus delta t. Okay. Our denominator is just going to be delta t. Those are the easy parts. Okay. Now, let's subtract those two numerators. This is a 2t minus, what's the second part there? 2t minus 2 delta t, right? Got it? That's the numerator of that fractional form there. But notice what we have here. 2t minus 2t goes to 0. So our numerator now is minus 2 delta t. Do you buy that? Okay? Now, can you see right now that this has a delta t in it and that has a delta t in it? And you can just divide them out? Okay, we'll do that. I like getting rid of those delta t's because that was a 0 in the denominator. So what are we left with? The limit, as delta t approaches 0, of a minus 2 over t times t plus delta t. Now, right? Now, can you take that limit? All right, the 10 o'clock scholar. All right, good deal. I've got to find you. I know you're in here. There you are. Okay. Elijah's here. I didn't think they had thrown you out yet. Okay. All right. Now, can you take that limit as delta t approaches 0? What does that give you? Negative 2 over t squared. That's it. Negative 2 over t squared. Everybody see that? I know what Jeremy's thinking. Sick thoughts. I mean, no. He's thinking, what if I had written this had y of t equal to 2 times t to the negative 1. And then what if I had tried to use my y prime of t, do my negative 2, t to the minus 2, which would be negative 2 over t squared. My goodness, you did it again, didn't you? So it works not only with polynomials which have whole number exponents, it works with fractional forms like we saw in the last example where you have fractional exponents, and it also works with negative exponents. So yeah, you can use that same rule you came up with, and there we have it. And now you'll never want to do another limit again, will you? No, we still have to. See how it works? Pretty nifty, huh? This differentiation not too bad, is it? Until we get some harder ones. Okay. Let's see if we can find some. Okay. But not yet. Okay. We'll first go to, now we already did example 3, so I'm just going to do through these. Differentiability and continuity. Now, do you remember what of course we remember what differentiability is, right? We were just doing that. It's defined as a limit as your delta x is approaching 0 of f of x plus delta x minus f of x over delta x. Difference quotient, right? Now, what was continuity? How do we define it? It's continuous at a point if it's continuous from the left, I mean, the limit from the left is equal to the limit from the right. Okay, and is defined there. Okay, so they both sort of deal with limits, and we love our limits, right? First test, yes. Oh, and by the way, anyone who came in late, before you leave today, pick up a test. If you didn't get one last week, Wednesday, then pick up a test for chapter 1, because we're in chapter 2 now. Okay. So the alternative form, limit form for a derivative, oh boy, I knew they were going to get to this at some point. This is where they're bringing it up. And now they're going back to the C's too. But remember, f prime of C was f of C plus delta x minus f of C over delta x. Well, okay. Let's start with the picture. That'll be the easiest way. It was derivative of f at C, f prime of C, that's what we're dealing with here, is f of x plus delta x. Okay, here's your delta x down here. X minus c is your delta x. Alpha of x plus delta x minus alpha of c, okay, and divided by x minus c, okay, or your delta x down here. Well, the difference here is alpha of x minus alpha of c. This is c alpha c, so that's just x minus c. So here is the alternative form for the derivative. It's useful for investigating relationship between differentiability and continuity. I still don't like to just throw this at you. Let me suggest this. What we were calling delta x before, according to this picture here, was x minus c. Wasn't that our delta x before? The change in x here was our delta x, right? Okay. So that was what we're calling delta x. Okay? And before we said f prime of c was the limit as delta x is approaching 0 of f of c plus delta x minus alpha of c over delta x. That's what we did before. That's why I started to say that, and then I thought, I wish I had gone with my first impression here. Okay, so delta x is equal to x minus c. Okay? So, this is what we did before when we put a c in here. This is how we did it, right? Okay? We're used to that. With this in mind, that your x minus c is your delta x. Okay? Now I'm going to do a couple of things. This is called the shell game. Okay? See if you can follow what's going on here. Okay? If delta x is approaching 0, that means 0 is approaching x minus c, right? And what if you added wish I'd have said it a little differently, but still. This would be the same as adding c to both sides, okay, and that would give you c is approaching x, but that's the same as x is approaching c, right? They're coming close to each other, so x is approaching c. So you see this delta x, that means that, okay? Now, let's do this part. Let's add c to both sides, and not this anymore, but c. And what you have down here is delta x plus c is equal to x. Now, that seems a little bizarre, right? So your f of c plus delta, I did things a little backwards here. Yeah, okay. This is f of x, isn't it? Because if here you added c to both sides, if c plus delta x is equal to x. C plus delta x equal to x. So f of c plus delta x would be f of x. Okay? So your f of c plus delta x in this form becomes f of x in that form. Okay? And as x is approaching c, alpha of x is approaching alpha of c. Okay? Well, I mean, we already have the alpha of c, so that's good. And the delta x then is x minus c. So you see, everything is worked out the same. That's saying the same thing. As the delta x is approaching 0, x is approaching c, and these are exactly the equivalent forms. Okay? As long as the limit exists. Okay? So, those are the same forms. Hopefully, I didn't screw it up so badly it makes it more confusing than it is already. But they are the same form. Note that the existence of the limit in this alternative form requires the one-sided limit. In other words, as x approaches c from the left-hand side, this is supposed to have a limit. As x approaches c from the right-hand side, that's supposed to have a limit. And if those limits are the same, they both exist and they're the same value, then we call this a continuous function. Okay? These one-sided limits are called derivatives from the left and derivatives from the right. Stand up, sit down, fight, fight, fight. No, that's nothing else. Okay. So it follows that f is differentiable on a closed interval a to b when if it is differentiable on the open interval a to b, and when the derivative exists from the right at a, no, from the right at a and from the left at b, if they both exist. Okay. Quite a mouthful there, but it does work. So let's see. That is the kind of the middle of page 105, the bottom part of the middle of 105. Okay, and then they go to this function they love so much. Okay, when a function is not continuous at some value x equals c, it is also not differentiable at x equals c. There they snuck something in on you, which is very, very important. When a function is not continuous at x equals c, it cannot be differentiable, ever. Okay? Now, back up just a little bit. That doesn't mean that just because it is continuous that it's also differentiable. But if it's not continuous, there's no way it's differentiable. And here's our good old greatest integer function. Not continuous at x equals 0 or x equals any integer. Not continuous at any interval value of x. Ever. Okay? So therefore it can't be differentiable there. Okay? Now the interesting thing is the limit of the derivative here would be 0, and there would be 0, and there would be 0, and there would be 0. But at the point, it's not differentiable because they don't have the same value. Okay? So, greatest integer function, it's not differentiable because it's not continuous. Okay? So, all right. And here's how they check that at x equals 0. And if you come to 0 from the left-hand side, from the lower side, that'd be f of x minus f of 0 over x minus 0. Well, the greatest integer function on this side would be your minus 1 minus 0 over whatever value that would be, not quite the 0 or something. That would be an infinite value, okay? Because this would be a minus 1 minus 0 over something going to 0. In fact, it looks like that should be a minus infinity there. And the limit as you approach 0 from the right-hand side would be, I think they got this backwards. Okay, no, that would be 0 minus 0, yeah, divided by x minus 0, and that would be 0. Okay. I still think the top one really needs to be a negative, but it will not necessarily. Although this is true that differentiability implies continuity, the converse is not true. Okay, that's what I was saying before too. Just because something is differentiable, that means it's got to be continuous. But just being continuous doesn't mean that it's differentiable. That is, it's possible for a function to be continuous at x equals c and not differentiable at x equals c. Can anyone think of an example of a function that's continuous at x equals c but not differentiable there? Unless you're used to thinking about them, don't get all bent out of shape if you can. But does anyone know what function looks like this? Absolute value function, okay? Continuous everywhere, right? But not differentiable at 0. Because coming in this way, the derivative this is negative slope, -1. And going up this way, it's a +1. At 0, it's neither. I mean, it's -1 from the left, +1 from the right, send upside down. It doesn't happen. Okay, let's see if they give that as an example. Ah, yes, they do. Look at them. Except they did absolute value of x minus 2. Just absolute value of x would have worked. This is not, it's a continuous function everywhere, including x equal 2, but its first derivative is not, because the slope here is a -1, the slope here is a +1. What's the slope there? Neither, okay? It's the limit coming in this way is a -1, the limit coming in this way is a +1. They're not the same. Not differentiable at x equal 2, because the derivatives from the left and from the right are not equal. So yeah, absolute value function, whatever you put in the middle of that, you can find the point that's not going to be differentiable. Sorry. I'm running out of gas awfully fast here. Okay. Oh, and this is example 6. I should be taking a bit more time with it, shouldn't I? I was just using it. By the way, at larsoncalculus.com, you get an interactive version of this type of an example. But let's see those one-sided limits. The limit as x approaches 2 from the left-hand side would be f of x. As 2, x is going to do that would be don't do that. Okay, remember here's our function. F of x is equal to absolute value of x minus 2. Okay, so f of x is equal to absolute value of x minus 2. Okay? Now, so as x is approaching 2 from the left-hand side, what is f of x minus 2? F of, as x is approaching 2. F of 2, I'm sorry. Is x. Say again? Okay. Well, f of x minus f of 2. As x is approaching 2, that's, well, this is absolute value of x minus 2 minus 0, because f of 2, when x is equal to 2, that's 0. Okay? Over x minus 2. Okay? Well, absolute value of x minus 2 when x is approaching 2 from the left-hand side, that's something just a little bit less than 2, right? But x minus 2, that's, but then you take an absolute value, and that's going to be something slightly positive. This is going to be slightly negative. That's going to be 0, so you have the same value, but this one's positive, this one's negative, that's going to be a -1. Okay? Closer you get to x equal 2, it's still going to be, as x is approaching 2 from the left-hand side, this would be like 1.999. Minus 2 would be negative 0.0001. So this would be, about absolute value of that is 0.0001. That's still going to be negative 0.0001. Those are the same value, only this one's positive, that's negative, that makes it negative. If you approach it from the right, alpha of x is going to be, x is greater than 2, right? You're approaching it from the right-hand side, so this is going to be positive, that's going to be positive. Positive minus 0 over positive is just going to be the same value, that's going to be a plus. In other words, the slopes are -1 from the left, +1 from the right. Okay? So much easier to just think of it as the slope of a straight line, and you got it. Okay. So f is not differentiable at x equal 2, though it is continuous at x equal 2. The graph does not have a tangent line at the point 2, 0. Can't happen, because it's here, here, can't have a different value down there. All right. A function that is not differentiable at a point at which its graph has a sharp turn or a vertical tangent line. Okay, a function that is not differentiable at a point Is that a sentence? A function that is not differentiable at a point at which its graph has a sharp turn. That's not a very good sentence, is it? I think it should be a function is not differentiable at a point at which its graph has a sharp turn or a vertical tangent line. I think that that is out of place there. Or else I'm just misreading it. Okay. So, here's theorem 2.1. Okay. Yeah, they put an extra that in there. Differentiability implies continuity. If a function is differentiable, it's got to be continuous. If f is differentiable at x equals c, then it's got to be continuous at x equals c. However, the reverse is not always the case. If f is continuous at x equals c, it does not guarantee it's differentiable. Most of the time it is, but it doesn't always have to. The relationship between continuity and differentiability is summarized below. If a function is differentiable at x equals c, it's got to be continuous at x equals c. So differentiability implies continuity. However, on 2, it is possible for a function to be continuous at x equals c and not be differentiable. So continuity does not always imply differentiability. Okay? So that's your thing. Most of the time, continuous functions are differentiable, but not always. If they have, and let me just go over a couple of phrases here. We saw in the absolute value function, that's what we call a point or a corner. There are other functions that might go like this. That one's called a cusp. Not going to be different. It's continuous, but not differentiable. And then, like the square root function, it's continuous from 0 to infinity, but it's not differentiable at x equals 0 because there's your vertical tangent line. And basically, the cusps are usually vertical tangent lines too. The points are not necessarily. Okay. So those are the 3 type situations you could have. All right. We did example 6. They did not show example 7. Sucked. They don't leave me any room to work any examples. Let's see. I'll do it here. Let's see if we have time. The function f of x is equal to x to the 1/3. Okay, is continuous at x equals 0. Do you agree with that? It's a cube root function, which is defined everywhere. Unfortunately, let's see if I can get this graph to look right. It looks something like that. Okay? If you think of the cubic function goes up like this and like this. That's the inverse of it. So it comes up like this, like that. Is continuous everywhere, including at x equals 0. Okay? Now, let's do that new alternative form, the limit as x is approaching c, and here our c is 0, of f of x. Make sure I say it right. The new form is f of x minus f of c. And the c was 0 over, I can't write, x minus 0, which is just x. Okay? Yuck. Okay. Okay. So this will be x to the 1/3 minus 0 over x. Okay. All right. That's going to be the limit as x approaches 0. What is x to the 1/3 over x? How's another way you could write that? Second? Okay, yeah, you could write it there, but let's keep the fractional exponents. Because what's the rule for dividing exponents? Second? Subtract the exponents, right? So that would be the limit as of x to the 1/3 minus 1, right? Which would be the limit as x approaches 0 of x to the minus 2/3, right? Which would be the limit as x approaches 0 of 1 over x to the 2/3, right? Now what kind of form is that? Is that an indeterminate form? No! That's an undefined form. No way that limit's going to exist. At all. No way. Okay? So yeah, that limit doesn't exist there. Why? What do you have at x equals 0? Vertical tangent line. The slope does not exist. Okay. And that's what they mean. Their picture's a little prettier than mine. We got it. Okay. And I think we just run out of time, but let me give you a few homework examples. Exercises. Do number 5. Do number 7. Both of those are at calcchat.com. Do any of the odds 9 through 13, but all those are at calcchat.com. Number 11 is at calcview.com. Do any of the odds 15 to 27, all those odds are at calcchat.com. Number 17 is at calcview.com. Do any of the odds 29 to 35, all of those odds are at calcchat. 31 is at calcview. Do any of the odds 37 to 41, they're all at calcchat, but only 37 is at calcview. Do any of the odds 43 to 47, they're all at calcchat, but none of them at calcview. Do either 49 or 51, or at least think through those. You don't have to do too much with them, but that's I guess they're both at calcchat also. Do 53, it's at calcchat, okay? Either 55 or 57, both are at calcchat, but 57 is at calcview. Do 59, do 61, both are at calcchat. Do 63 or 65, they're both at calcchat. Do 67, then do any of the odds 69 to 75, they're all at calcchat, but only 69 is at calcview. Do either 77 or 79 or both, they're both at calcchat, but 77 is at calcview. Do either 81 or 83, they're both at calcchat, but not at calcview. And then do any of the odds, no, do either 85 or 87, they're both at calcchat, only 87 is at calcview. Goodness gracious, do 89, 91, and if you want to think through true, false, 93 or 95, Don't expect those on tests, but they're still good things to think through. 97 is a pretty good problem, and that's it. Goodness gracious, quite a few of those. All right, before you go, let me make sure everybody has a copy of the first test. And you need one? All right, I gave you one. You need one, right?
Yeah.
All right, good deal. The test will do 1 week from today. You can have longer if you need it, but that gives you a day to come back and ask questions. Now, I won't work a problem for you or work anything like it from the text, or I'll clarify the problem. And here's Justin. Did you get a copy of the test? Okay. If you'd have come in a little sooner, I could have counted you here. All right, good deal.